Let's talk about the hidden world of fluid mechanics. And look, forget everything you remember from dusty textbooks. This is the invisible script that dictates, well, pretty much everything, from the weather patterns on our planet to the sleek design of a Formula One car. It's literally everywhere, and we're about to pull back the curtain.
Okay, so let's just jump right in with a question that seems to completely defy logic. You've got this massive steel ship, right? Hundreds of tons, just floating there effortlessly. But then you toss a tiny little pebble off the side, and poof, it sinks straight to the bottom. How on earth is that possible? Well, the answer is hiding in the very fluid that ship is sitting in.
So to even start to solve that puzzle, we have to ask a really basic question: what even is a fluid? And here's the first surprise. It's not just liquids. A fluid is any substance, liquid or gas, that doesn't have a fixed shape and just kind of gives into pressure. Put simply, if you push on it, it's going to keep moving and deforming. Now, of course, not all fluids are created equal. And the first really crucial property we need to get our heads around is viscosity. The best way to think about it is as the fluid's own internal friction. Its stickiness. This one property determines how easily a fluid flows. And this is the perfect way to picture it. Just think about pouring honey versus pouring water. Honey has a super high viscosity. Its molecules really cling together, so it flows very slowly. Water, on the other hand, has a very low viscosity. It has almost no internal friction, which lets it flow quickly and easily. I mean, this single property is why everything from thick, slow-moving lava to the fast-flowing gasoline you put in your car behave the way they do.
Okay, so this might sound a little strange, but fluids don't actually have to be moving to be powerful. In fact, when we look at fluids that are just sitting still, what we call fluid statics, we find some of the most incredible and useful forces they exert. And yeah, this is where we start to find the answer to our big ship problem.
It all comes down to one simple rule for fluids at rest. Pressure goes up the deeper you go. Anyone who's ever dived to the bottom of a swimming pool has felt this in their ears, right? It's the weight of all that water above you pressing down. The formula is pretty straightforward. Pressure is just the fluid's density times gravity times how deep you are. The deeper you go, the more intense that force becomes.
And all that pressure leads us straight to this, the legendary Archimedes Principle. This is the big eureka moment. What it says is that any object you put in a fluid gets an upward push. We call this the buoyant force. And that upward push is exactly equal to the weight of the fluid the object pushed out of the way. So you see, floating is literally a battle between two forces. You've got gravity pulling the object's weight down, and you have the buoyant force pushing it up. A giant ship floats because its huge, hollow shape displaces an enormous amount of water. And the weight of all that water is actually greater than the weight of the ship itself. So buoyancy wins. The tiny pebble, though, it's really dense and displaces hardly any water. Its weight is way greater than that tiny buoyant force. Gravity wins, every time. Okay, so we figured out fluids sitting still. But what happens when we get them moving? Well, that's when things get even more interesting, and it turns out their movement isn't random at all. It follows a really precise set of laws that we can actually predict and use. And the first big rule of motion is the continuity equation. It's really just a way of saying you can't create or destroy the fluid. What goes in must come out. You've actually seen this in action a million times. Ever put your thumb over the end of a garden hose? You squeeze the area the water can flow through, so to get the same amount of water out, it has to speed up, right? It creates that powerful jet. Squeeze the area, speed goes up. Simple as that.
And that simple relationship, that link between area and speed, leads us directly to one of the most incredible and powerful secrets in all of physics. This is the principle that lets birds and jumbo jets fly, and it's what helps race cars stick to the track at crazy speeds. And here it is, Bernoulli's principle. The core idea is so simple it's almost hard to believe. It says that faster-moving fluid exerts lower pressure. That's it. It's an inverse relationship. Where the speed is high, the pressure is low, and where the speed is low, the pressure is high. This one simple fact is the absolute key to generating lift. So how does this get a 300-ton airplane off the ground? Well, look at the shape of a wing. It's designed so air has to travel a longer curved path over the top than the flat path underneath. To get to the back of the wing at the same time, the air on top has to speed up. And what did we just learn? Faster air means lower pressure. So you've got low pressure on top and higher pressure from the slower air below. And that difference creates a massive upward force. That's lift.
But hey, it's not all about these subtle pressure differences. Sometimes you just need raw brute force. And that's where the momentum equation comes in. This is basically just Newton's famous second law, F equals ma, but for fluids. It tells us that to create a big force, you have to change the fluid's momentum in a big way. This is exactly how a rocket engine works. It's just throwing a ton of mass out the back at an insane velocity to generate a huge forward thrust.
So far, pretty much everything we've talked about has been in a perfect, ideal world. But in the real world, well, things get a bit messy. We have to deal with that stickiness we talked about at the beginning, viscosity, and the friction that it creates. So, to predict how these real, messy fluids are going to behave, engineers use this amazing tool called the Reynolds Number. Don't worry about the formula. What's important is what it is. It's basically a ratio that compares a fluid's tendency to just keep moving versus its tendency to stick together. And this one number can tell us if the flow is going to be smooth and predictable or totally chaotic.
And what that number predicts is whether you'll get one of two things. At low Reynolds numbers, you get this beautiful, smooth, orderly flow we call laminar flow. Think of how thick syrup drizzles slowly. But crank up the Reynolds number and the flow becomes turbulent, a chaotic, swirling mess of eddies. Think of a raging river or the smoke curling up from a blown-out candle. Controlling that switch from smooth to chaotic is absolutely critical for designing just about anything that moves through a fluid.
And that messy, turbulent flow? It has a very real cost. As a fluid tumbles through a pipe, it's constantly rubbing against the walls, and that friction basically acts like a brake, stealing energy from the system. This is a massive problem for engineers. It's the reason cities need these gigantic pumping stations just to push water to our homes. They're constantly fighting to overcome all that energy being lost to friction, mile after mile. So, from a ship floating on the ocean to a plane soaring through the sky, from a simple garden hose to the blood pumping through our very own veins, the principles of fluid mechanics are the invisible forces that shape our reality. It really is the hidden script of our world. So the question is, now that you know a little bit about that script, what are you going to see differently?